So welcome to the fourth lecture in this series. So in this lecture we will discuss more about the intricacies of routers and how to make the router pipeline more efficient, and then time permitting we'll also discuss how the cache subsystem and NOC are supposed to be co-designed. So we recall that in our previous lecture we had discussed the first three stages, which is buffer write. This is mandatory for all flits in the sense that they need to be written into buffers first before processing. Then this was only for the head flit, the next two stages, where we perform route computation. So route computation, we basically figured where do you need to go, north, south, east or west, and given that the physical channel has been decided, we then allocate the virtual channels. So we do VC allocation over here. Just give me 1 second. Yeah. So we do VC allocation over here. So we discussed these three stages. So two more stages are remaining. One is the allocation of switch ports. So here we reserve a path to the output port. Here fairness is important. We will discuss this majorly here. And then switch traversal, which is not a big deal, which basically means that we need to traverse the switch once the connection between the input and output has been made, and this is done. So then we release resources. So let's discuss more about switching. So if you would recall from the previous lecture, we have 10 inputs. If we are assuming 2 VCs per physical channel, because the physical channels are north, south, east, west and local, so 5 into 2, 10, and the outputs are 5. What are those 5? The outputs are basically north, south, east, west and local. So it's a 10 cross 5 switch. So there are many ways of making a 10 cross 5 switch. We could go for bigger switches. So we could go for switches of this type that have the 10 inputs divided like this, a 5 cross 2 switch here, a 5 cross 2 switch there. So 5 here, 2 output, 5 here, 2 output, and this is 4 cross 5. So you think about it, there is some amount of internal quenching, in the sense this could be a bottleneck, because in principle, all 5 outputs could be used, but we are kind of creating a bottleneck over here. But again, this is one design option. Another design option could be we have many of these 2 cross 1 switches, and then we connect a 5 cross 5 over here. So then, the other issue is that if, let's say, all 4 of these are empty, then both the requests could possibly go along different routes. This could maybe go along here, but we are precluding that possibility. So there is always a trade-off, right? Big switch, small switch, how they are connected, this trade-off is always there. So let us now have some metrics, right? Some sort of a metric to quantify the latency and area of a switch. So this is more like a thumb rule, right? It's not a metric. It's more like a rule of thumb that can be used to kind of get an approximate estimate, right? Not an exact one, but an approximate estimate. So in this case, for an M cross N switch, if you think about it, we have N inputs over here, N over here. So pretty much the traversal that is happening, right, the latency, we are like traversing N points here, M points here. So the latency is approximately M plus N, arbitrary units of course, and the area is M multiplied by N, again arbitrary units. So if you look at a single level 10 cross 5 switch, its area cost is 50 and latency cost is 15 as per these formulae. So now if we have 5 2 cross 1 switches and then we have 1 5 cross 5 switches, so basically the area cost will be much lower. The area cost will be 13 and the area cost will be 35 and the latency cost will be 13, right? So this is the big switch design which is over here, and we go with the small switch design, which are several of these smaller ones and 1 5 cross 5. Then here basically I'm sorry. So this is the small switch design. Sorry, I went the other way. This is the small switch design. where we have these 5 2x1 switches. So this was, so in this case for the small switch design, the area cost is 35, the latency cost is 13. But for the big switch design, which is 2 5x2 and 1 4x5, the area cost is kind of in between, but the latency cost is very high. And hence, this is not a good design because, the smaller one was actually better. It was faster and the area was also lower. So as you can see, there is a very complex optimization space if we have like 2 levels of switching with regards to what is the best. And of course, we could go even one step further and have 3 levels. So then the optimization space will become even more complicated. So now let's now look at a special kind of switch called a dimension sliced switch. So this is used for XY routing. So in this case, what happens if you take a look at this? The switch at the bottom, the inputs are east, west and local. And given the fact that, so it's XY routing, right? So if you're coming from the east or west, you would still go along the Y axis. So that's the reason there is one connection for all the messages that want to go along the Y axis. There is a connection to another switch which is smaller. But we are assuming again that we will not have a lot of such messages because in a large network with XY routing, most of the time you will be traversing only along the X axis or only along the Y axis. That's the reason there's only one arrow, and finally, you could, in this case, you could emerge along east or west. Or if you want to go to north, south and local, then any message along the X axis can go to the switch at the top. The switch at the top, the only inputs are north and south. So kindly recall that if you are coming from the north or south direction, which is pretty much along the Y axis, you cannot make a turn to the X axis. From X you can go to Y, but from Y you cannot come to X. That is not possible. Given the fact that you cannot come to the X axis, right, the only outputs are either continue going north or south. And for all the messages that are coming from here, they also get routed. So you either go to north, south, or you go to local. So this, in a certain sense, is reasonably efficient. So here, basically, because of this asymmetry, let's compute the area cost and the latency. So look, if we are going from north to north or north to local south, the latency here is not much, it's only 8. And the latency here is only 9 units. So of course, worst case it is 17 units if you are going this way, if you are making a turn, that is. But given the fact that turns are very rare, the latency is, you'll actually in XY routing you'll only make a single turn, right, if at all. So the point is that in most cases latencies are 8 or 9, which means it's very fast. And if I look at the area, so this would be 15 and this would be 18, so the area cost would also be 33, which if you just look at the previous figure, 33 is a much smaller number. I repeat, 33 is a much smaller number than these numbers, 35, 40, 50, etc. And of course, the latency cost, which in most cases is 8 or 9, again, this is a much smaller number. So the key idea is that we have been able to design a circuit where the insights are given here. No turns are allowed from north, south to east, west. Hence, this is a one-way arrow. Nothing can come from here to here. The lower router would send flits in a horizontal direction, or for an XY turn would send it here. And the upper router can only send it either straight or to the local tile. So with these insights, as you can see, we were able to design a switch which is more efficient. Undoubtedly, it is more efficient. And basically, it is kind of co-designed with the routing protocol, which is a good thing. It basically allows us to kind of look at the protocol and the switch together and basically mutually optimize them. So let us now discuss allocation and arbitration, which takes things one notch higher. So we first looked at switching, but along with looking at switching, we would also like to look at this process of switch allocation, VC allocation, right? So we'd also like to look at these things. So the difference between an allocator and arbiter is kind of fine. So an arbiter chooses 1 out of n requests for resource allocation. So if there are n requests for resource allocation, the arbiter would just basically choose 1. An allocator on the other hand would choose a subset of n requests and map them to resources, or in other words, it would create a one-to-one mapping between n requests and m resources. So if there are requests over here, resources over here, it would kind of create a mapping between them. That is an allocator. So then allocator, of course, a trivial idea would be that you chain together arbiters in the sense that for the first resource, right, you map one of the requests, remove that request from contention, then for the second resource, so on and so forth. But there are ways and methods of creating custom structures which are far more efficient. So the matching between resources and requests is somewhat interesting and theoretical. So again, I would like to go back over here. An arbiter chooses 1 out of n, and allocator does the matching of requests and resources. So the matching is a somewhat theoretical problem, but this is how it can be explained. Let's say that I draw a bipartite graph. What is a bipartite graph? Well, the resources and the requests are on 2 lines, right? There is no arrow between 2 resources and 2 requests. So the request in this case is R1, R2, and the resources, this is the request and this is the resource. So every request is mapped to at most a single resource. That is the first condition, that a request cannot be mapped to 2 resources. The second condition is every resource is mapped to at most a single request, which means a resource also cannot be mapped to 2 requests. If request Ri is mapped to resource Sj, then this basically means this function f Ri Sj is true, right? The f Rs function is true if request R. So the idea is that only if f Ri Sj is true, then only the request Ri is mapped to resource Sj, or in other words, the f Rs function basically denotes an interest function, that a request R is interested in resource S, right? So the f Rs function is true if a request R is interested in resource S, and then only you can map the request and the resource together. You cannot map a request to a resource that it is not interested in, right? So what you do is that with these 3 conditions in mind, we draw a bipartite graph with the requests here and the resources here, and there is a dotted line between requests and resources, which essentially indicate that there is no mapping, but request R2 is interested in 2 resources S1, S2, and R1 is interested only in S1. So what we could do is we could make a matching which is suboptimal, in the sense R2 could be mapped to S1. If R2 is mapped to S1, we can't clearly do any more matches because R2 is taken, right? S1 is taken. R1 was interested in S1, but R1 can't get mapped to S2 because it was never interested in S2. So this matching that you see over here is maximal, in the sense that we cannot convert any more interested edges to matched edges, but it is not maximum, right? We will see a maximum exists. The maximum is over here where we map R1 to S1 and R2 to S2. So in this case we have 2 matchings, whereas in this case we have only 1, right? And this basically indicates that this is maximum. Anything maximum is also maximal, but in this case in the previous case, which is this one, we see that this is not maximum, only 1 is being mapped, but it is maximal in the sense we can't make any forward progress. So suboptimal matchings can be maximal, but an optimal matching is always maximum and consequently maximal. So our aim is of course to match as many resources to requests as possible, which means computing a maximum matching in hardware in real time, which of course is difficult, but thankfully our requirements are not that deep that we would actually need to go to that level and have a really optimal solution, because number one, we are not dealing with too many resources over here. We are dealing with a limited number of resources, and that is why we will see that interesting and good and efficient and effective hardware algorithms are possible. So now we will discuss a couple of arbitration and allocation mechanisms. Given the fact that we have seen the overall space, the simplest idea is the round robin arbiter, which is a simple circuit that you can see over here. In this case, we have basically 3 requests and we have a single resource. We have request lines and a grant line. So basically, request has to be 1, which essentially indicates that request 1 is granted the resource, right? So request indicates interest, and then we have a round robin scheme. So first it is you assert grant 1, then grant 2, grant 3, then again grant 1, grant 2, grant 3, so on and so forth. So let us assume that let us assume a base case where none of the grant lines are 1, all of them are 0. So if all of them are 0, then the output of the NOR gate is 1, the output of this is 1, right? And basically this, as we said, grant 3 is 0 over here. So if the value of the priority 1 is, let's say, P1, then P1 and 1 is going to be P1, P1 or 0 is going to be P1. This is a D flip-flop. So essentially it is going to maintain its value, right? So essentially whatever is the value of the priority, so priority can either be 0 and 1, right? So in this case, if we say that the priority is equal to 1, over here it will just maintain its value. Whenever, say if request is 0, the grant line is 0, but if request is 1, then 1 and 1 together will make the grant line 1, which means the first request is granted. The moment the first request is granted, let us see, a lot of things will happen, a lot of things will change, right? So as I said, when no request is granted, all of these D flip-flops maintain their status quo, right? When no request is granted and no request is also 1, all of them are 0, all of them will maintain their status quo. But the idea is that the moment we decide that, we will grant one request, because, the priority here was set to 1 and the request 1 line just went from 0 to 1. So 1 and 1 ANDed will become 1, right? So in this case, what we do is that grant 1 becomes 1. So the output of the NOR gate becomes 0. The output of the AND gate thus becomes 0. And given that grant 3 was 0 anyway, so this becomes 0 and this becomes 0 and grant 1 becomes 0. Right? So what we basically see is that in one cycle, if grant 1 is equal to 1, then in the next cycle, it basically becomes 0, because why? Because the output of the NOR gate becomes 0, which makes this 0, and grant 3 anyway was 0 to begin with. So then in the next cycle, 0 gets written into this D flip-flop. So basically priority 1 becomes 0 and grant 1 becomes 0. Alright, so basically this means that one request was granted 1 for one cycle and then it lost its value. But now let's see what happens. So let us again look at the previous cycle when grant 1 was 1. So in this case, again, if grant 1 was 1, this is 0. The output of the AND gate over here is 0 because one of the inputs is 0. If I if I compute an OR between 0 and 1, this becomes 1. And this basically means that in the next cycle, of course, the priority for request 1 becomes 0, but the priority for request 2 becomes 1, right? Because the D flip-flop value at the negative edge gets transferred from here to here. The moment that happens, this gets set to 1, And if request 2 is 0, then this grant line is 0 anyway, this was 0 to begin with. If this is 0, this is 0, so this status quo over here is maintained. But the moment request 2 becomes 1, then 1 and 1 get ANDed and this becomes 1. So for one cycle, the second request gets to access its resource. And then the same process happens, that again, here grant 2 becomes 1. So then the output of the NOR gate becomes 0. So this becomes 0. And again, the grant 1 line was 0 to begin with, right, in this case. So then what happens is this becomes 0 and finally this becomes 0. So then so on and so forth. So this is like a token that is being passed from grant 1 to grant 2 to grant 3, again back to grant 1. So what we are essentially seeing is that this is a typical round robin allocation scheme where you first allocate the resource to the first request. Of course, if it's not interested, you wait till it is interested, then you allocate it, then it comes to request 2. You wait till it is interested, then it comes to 3. Again, you wait till it is interested. Once it is done, grant 3 will become 0 and grant 1 will become 1, subject to request 1, but at least priority 1 will become 1, right, the moment grant 3 is set to 1, right, and that is mainly because this becomes 1, so this becomes 1, so this becomes 1. So this is a classic round robin scheme where it's like a token that flows from request 1 to 2 to 3 to 1. And of course, if one request is not interested, we wait until it is interested. Once it is, we use the resource for one cycle and then the token goes to the next request, right, as per round robin order. So of course, this is a nice and simple scheme in the sense we could draw the full circuit very easily on the screen and it's easy to understand. Of course, there is no way of enforcing a priority between requests because we follow round robin. Second, let's say if an agent is not interested, it still has to be given a chance. It's not given a chance. It has to be given a chance because it basically needs to use the resource, or let's say not use the resource, but at least get the permission to use the resource and then hand over the permission to the next in line. So if you think about it, given the fact that we have a strict round robin order, you have to be interested. Even if you are not interested, you'll still get the token and you will have to pass it on. We can have another scheme which is again, conceptually not very different from round robin if you would ask, but the idea is that there is there is a small difference in the sense there is a notion of priority here, right, which makes it quite interesting. So in this case, what we do is that we are still looking at a single resource kind of scenario where all our agents who are our requesters, they are arranged in the matrix form. So you have n agents, let's say n requesters, then an n cross n matrix, and if let's say so it's a Boolean matrix, so let's say the ijth entry is equal to 1, this would basically mean that agent I has a priority over agent j. So it's the same, agent and request is the same, so it's basically that a certain request has a priority over some other request. The ith request or ith agent, as we are calling, has a priority over the jth request or jth agent. So then what happens is, if a given agent is not interested, then what it does is it sets all the entries in its row to 0. So it sets everything to 0. And all the entries in its column to 1, of course, other than diagonal entries. So diagonal entries don't matter. So this is basically like saying that, look, everybody else has a higher priority than me, right? So for that, I set my row to 0 and column to 1, because the idea basically is that you want to look at kind of a row and its transpose. So basically what you do is you say that, look, if I am the ith agent and basically all the entries in my row are 0, I don't have higher priority than anybody else. and if all of the entries in the ith column are 1, that means everybody else has a higher priority than me. So in every cycle, the request is granted to the agent, which has 1s in all of its entries in its row. So basically, who gets it? If you have 1 in all of your entries, again the diagonal element doesn't matter, right? If you have 1 everywhere, you are basically granted the request. The request is granted. This basically means that you have a higher priority than everybody else, and we maintain the transpose property. So basically, it is always the case that if this is a matrix A and we are looking at non-diagonal elements, Aij, which means is basically the knot of Aji, which basically means that if I has higher priority than J, then J has lower priority than I, and if I has lower priority than J, then J has higher priority than I. So this always holds, the transpose property always holds. So then the idea is that once I have the highest priority, I get the resource. So once the ith agent is kind of done servicing its request, it sets all the entries in its row to 0 and sets all the entries in its column, which is ith column, right? Ith row, ith column, let me mention that, to 1. This basically says that, look, I am done. Now I set all the entries in the row to 0, which basically indicates that I now have the lowest priority. Everybody else has a priority higher than me. So you people may go ahead. So this means it relegates itself to the lowest priority. But again, this mechanism is possible to generalize by saying that, instead of setting all the entries to 0, it will still maintain a few as 1, which indicates it is not relegating itself to the lowest priority, but somewhere in the middle, like an intermediate priority. That also is possible, and this approach allows that. But of course, you may then have problems of starvation, but at least this approach does in principle allow that. So the matrix arbiter, here is how it looks. So consider the state of the matrix for the first row. So we see that all of the elements are 1, barring the diagonal of course. And for the first column, all the elements are 0. So we are all set. The request can be given to it. So the resource can be given to it. So that's the winner. Once it is done, it sets all the entries to 0 in its row and all the entries in its column to 1. So now we have a new winner. In this case, it is request number 3, because this is the only request whose all the entries are 1. And you can also see the third column, all the entries are 0. So this clearly means it has the highest priority. After that, it too does the same. It sets the row entries to 0, column entries to 1. And we have a new winner again, which is request number 4. Same thing. It does exactly the same thing after releasing the resource, which is all 0 in its row and all 1s in its column. And finally, we have request number 2, which is the last to get. So it sets all the entries once it is done to 0, 0, 0, and these entries to 1, 1, 1. So you can see the state of the matrix is the same as what we began with: x 1 1 1, 0 x 0 0, 0 1 x 1, 0 1 0 x, right? So we again come back to this state. So we again basically in this case also we are having a round robin, but there is a notion of priority in the sense it's not strictly 1 2 3 4. We can change this initial state and we could have a different ordering as well. And also it's not we are not obligated to clear off everything in the rows or columns, in the sense we need not delegate ourselves to the lowest point, and also it is possible to alter this matrix in the middle. It's not like a logic circuit that maintains state. So let us now clean the ink and basically reiterate the message. So the message is that this is still a form of limited round robin, but given the fact that we are maintaining state, we can ensure a degree of priority. So let's now look at other forms of allocators. So let's look at a separable allocator. So here, as you can see, we have 9 request lines and we have 9 grant lines. So let Rij, so Rij, as you can see, there are numbers written here, there is I written over here, there is J written over here. So Rij means that the ith agent is interested in the jth resource. So basically, if there are 3 agents and 3 resources, right? So let's say there are 3 agents and 3 resources. Then what we will have is we'll have 3 cross 3 9 combinations, and this is what Rij would denote. So what we have over here is that we have these 3 cross 3 switches or boxes, and essentially for the first resource, the switch over here basically gets the corresponding request from the agents, right? Then it figures out that look, one of them needs to be granted, right? And it makes the grant. Similarly, this is for the second resource, this is for resource number 3. So this is an example of an allocator which is separable, where there are multiple agents, multiple resources, and a matching has to be done. This looks simple, but there is a problem. The problem is that it is possible that all the requests get selected for the same resource in the first column of switches. So it is possible that this column over here, so given the fact that one agent can only be mapped with one resource, all of them will say that look, okay, you are interested, you get mapped to the first resource. So then what will happen is this will be selected, this will be selected, this will be selected, ultimately this will choose only one, even though it is possible that let's say the first agent was also interested in the second resource, but this switch will not forward this request to here. As a result, you could have had more mappings clearly, but that would not have happened. So the matching in this case is not maximum, and as luck would have it, it is also not maximal. So let me tell you why it is not maximal. So let us say that the first agent is interested in resources 1 and 2, and the second agent is interested in only resource 1. So it is possible that this switch would basically, so at the first level, at the first column, that is, all the requests for resource 1 will be the ones that get selected. Essentially this will be 1 and the rest will be 0. And then this switch over here will basically choose the second request as the winner. So the winner will be chosen as the second. So in this case, as you can see, an additional match could have been made, in the sense you could have matched the first request with the second resource. This is something that could have been done, but this is not being done. So hence this is not maximum, it's not even maximal. So not being maximal basically means that an additional matching could have been done, but it is not being done. If I were to kind of draw it over here, with these being the requests and these being the resources. So what you can clearly see is that at the beginning, the first request is interested in 2, right? And right, so the first request is interested in 2 resources. The second request is interested in only 1, and this is only interested in this. So what we do is that if we grant this one over here, then it is clear that this is locked and this is locked. But then an additional granting or an additional mapping could be done, which is between this and this. But this is exactly not what is being done, in this case, if all the first requests are chosen, and which is why it's not really a maximal mapping allocator. And we would at least want our allocators to be maximal, if not maximum. Of course, maximum is preferable, but that is harder. So let's now look at a wavefront allocator, which in many ways is a very neat idea. It's a very neat and very interesting idea. So here the idea is that you consider an n cross n matrix. So n cross n why? So it is basically n agents and n resources, right? Or n agent slash request. So agent and request is the same. So we have n agents and we have n resources. And basically again we have these cells, right? So ij basically means that the ith row or the ith request is interested in the jth resource, right? So the ith agent is interested in the jth resource. So as you can see, 2 1 2 1 means I am I am in the second row, I am agent number 2, I am interested in resource 1. Similarly, this is 3 4 4 4, so on and so forth. So of course, if I am interested, I have a different color. If I am not interested, I don't have a color, I am kind of uncolored. So as you can see here, this is a matrix, it's a square matrix because it's n cross n, and some of these squares have a different color, which basically indicates that there is an interest. For example, this square would indicate that the third agent or the third request is interested in the second resource. This is what it would indicate. So now the idea is that we need to do a mapping, and this is the hardware. So we take all of these things. These are like, like kind of very, very small processing units with a tiny amount of logic, and they are connected in a torus shaped network. So this is essentially the subcircuit of our allocator. It's called a wavefront allocator. Why a wavefront? It will be very clear in the next slide. So the key point is that we give it 2 tokens. So the pinkish one is the row token, which only traverses along the rows, and the bluish one is the column token, which only traverses along the columns. So we start by giving a row and a column token to each diagonal element. So as you can see, in all the diagonal elements, we will have 2 tokens each, 1 row token and 1 column token. Then what we do is that we run this algorithm for multiple rounds. So in each round, we move the row token, right? The row token is the pinkish one. We move it 1 step to the left. So this goes 1 step left, this goes 1 step left, this goes 1 step left, which means it comes here. And we move the column token 1 step down. So the bluish column token goes down, this goes down, and again, of course, shows up over here, and this goes down, this goes down. So what will again happen is that the blue token will arrive over here. This is blue. This pink token will arrive over here. So again, you will still have a pair that is forming. Similarly, 2 tokens will collide here. So what we will see is that after 1 round, this will be the situation. So let us now remove the interested information, right? So this will come later, but this is just an example showing the movement of tokens. So initially, as you can see, all the tokens are on these diagonal cells. So this is like, a diagonal over here. Then if I move to the second round, as I said, the column token comes here, the row comes here, right? So basically at every point, again, the rows and column tokens collide and they form a pair. So this is something like, you can visualize, it's like this wavefront propagating in this direction. So you have a smaller wavefront here, and it's like the wavefront again, kind of showing up over here. So you will again have this situation here. Why is that the case? Because this row token would again come here, and this column token would come here, and they would collide. So this is, as you can see, it's like a wavefront that is propagating in this direction and kind of getting reflected and showing up over here at the other diagonal end. Now if I consider round 3, so this wavefront will propagate like this, which is nothing but, this moving in this direction, this moving in that direction. So then again we'll have a smaller pair of 2 here, and then another pair of 2 here. And similarly, then they will propagate in this direction, which is where, the wavefront will be over here and over here. And the final state will actually be round 1, where in the next round of propagation, we'll come back to this state. So why is this happening? So if you think about it, the tokens themselves are moving independently. The row token moves along the rows, and the column token moves along the columns. So the movement as such, or the movement per se, is independent. All right. But it appears, so it is like, these small waves of water where the molecules of course move independently, but it so appears given their synchrony, that a wave is propagating, a wave is rippling through, which is something that we get to see over here as well, right? So this is where the wavefront in the wavefront allocator comes. Now let us add this information that basically some of these cells are interested, which means the second request is interested in the second resource. Similarly, third request is interested in the first resource. So what happens is that if there is an interest, the moment both the tokens comes, mind you, I would like to do this, both the tokens have to come, the row and the column. So of course, needless to say, no cell will ever have two blue tokens or two pink, because they travel in perpendicular direction. See, if you have two tokens, one will be blue, one will be pink. The moment you have both, if you absorb them and remove them from circulation, it is as if a mapping has been created from the ith request or agent to the jth resource. So the moment the ijth cell absorbs both the tokens and removes them from circulation, it is as if a request resource mapping has been made. So in this case, what happens is that in round 1, well, what happened? So what happened is 2 was interested, so it grabbed both the tokens. So then what happened is that this token was absorbed, so the only downward movement was of this blue token over here, and similarly this token was absorbed, so the only movement was for this pink token, which kind of went over here. So now what has happened is that so now of course, as you can see, no cell has 2 tokens, that is, no interested cell has 2 tokens. Then we come to round 3, here again we see a situation developing. So what happens is this moves this way, this moves this way, so now we have both the tokens over here, and this cell is also interested. So in this case, both the tokens are grabbed and they are removed from circulation. So once they are done, as you can see, now we kind of have these interesting situation of single tokens each, and of course we have tokens circulating, but again no cell has 2 tokens, right? Or let's say no interested cell has 2 tokens. So as a result, 4 rounds are over and algorithm completes. We made 2 mappings. One was mapping 2-2, that was one mapping that we made. The other mapping that we made was 3-1. So those are the 2 mappings that we made, 2-2 and 3-1. Those are the 2 tokens that we grabbed. And those are the 2 mappings that we made. So what are the properties of this wavefront allocator? So once a token is absorbed, it is clearly put out of circulation. So that's not very hard to fathom. This means that no cell in the same row, which is the agent row or column, right, can get both the tokens. So this basically means that the entire agent row no cell can get, which means that this agent can't be mapped to any other resource, which is what we wanted, mainly because its row token has been put out of circulation. No other row token can come to it, and furthermore the column token has also been put out of circulation, so this resource cannot be mapped to any other agent. So this means that the matching that is produced is at least correct, which basically means that a request is mapped to at most a single resource and a resource is mapped to at most a single request. So at least this is visible from our token logic, which you can see over here, that because we remove them out of circulation, the row and column are kind of get blocked, and as a result it is not possible for the same row, for any other cell in the same row to actually get 2 tokens because the row token is gone, or any other cell in the same column to get 2 tokens because the column token is gone. So now let's look at some of the more important properties. So it produces maximal matching. So there is a proof in the book. So the idea basically is that if a matching is possible, then it's kind of shows up. So there is clearly no matching that could have been done but was missed, because the point is that every cell is getting its chance. In a sense, if you see, the wavefront is kind of propagating through every cell, even though every cell may not have 2 tokens because they may be put out of circulation, but the wavefront is traveling through every cell, so it is getting its chance. That's important. right? As we said, this mapping and matching are two synonymous terms that we will use interchangeably just for the sake of this discussion. I'm being slightly loose here, but that's hopefully in a good way. So every cell gets the two tokens at some point of time. If no cell in the same row or column has already been allotted its request, right? So if, let's say, in that row or column, no other resource or request has gotten it, then every cell will get both the tokens, and that is when it will absorb them and put them out of circulation. Which means at that point of time, the cell can be allotted the request, right? So there is no reason why that should not be done if the cell is interested. So what you can see is, unlike the previous case, in this case we don't miss a mapping, right? So a mapping which can legitimately be done, which basically means that the tokens are swimming around unabsorbed, such mappings are not missed. So we don't miss a mapping. So now we have kind of finished the wavefront allocator part. So we are now at kind of the cusp of our discussion where we would like to look at optimizations to the router pipeline. How can the router pipeline kind of be made more efficient, because 5 stages just to traverse a router appears to be too much. So given the fact that we are not happy with a router itself taking 5 cycles, and why are we not happy? Well, the main reason is that the hop to hop distance is, let's say, 10 hops or 20 hops, then it's 20 times 5, which is 100 cycles, right? So that's huge, right? Given the fact that access to the main memory itself is around 200-300 cycles, just moving from one point to the other point on an NOC, and that too it taking 100 cycles, is too much. That is why the router to router latency has to be reduced, and that will happen only when these 5 cycles actually come down. So where do we stand? So let's look at where we stand. We have 5 stages: buffer write, route compute. Once I've computed the route, I allocate a virtual channel, allocate a switch port, and traverse the switch, right? So these are the 5 stages we have seen. So let me draw a diagram like this, where the row basically means the stage. So this is slightly different from a pipeline diagram. We will see why. Because in the same stage, as we can see, different things can happen, right? So basically the flits are F1, F2 and F3 in a packet. So initially what will happen is F1, which is the head flit, will be there in cycle number 1, it will enter the router. Now let's say in cycle 2, this moves to the route compute stage because we don't expect any stalling here. So flit F2 comes here, and then flit F1, the route is being computed. After that, we go to the virtual channel allocate stage, where some stalling could happen, in the sense F1 is there in the virtual channel allocate stage. F2, however, will not move to route compute, it will stay in the buffer write, in the sense that the buffer of course has been written, but essentially the flit is staying there, mainly because its head flit has not progressed. So at this point of time, in the third cycle, we try to allocate a virtual channel to flit F1, but at that point we don't find a free virtual channel, so that's the reason we don't do anything. It's like a stall. Next, in the fourth cycle, we again try to allocate a virtual channel, and towards the end we are successful. That is why in the fifth channel, F1 goes to the switch allocate stage, and F2 still remains over here, because for F2 we don't have to compute a route, or we don't have to allocate a virtual channel, because these are mainly done or only done for the head flit. They are not done for body flits. So then what happens is that in cycle 6, we see that F1 has allocated a switch, so it traverses the switch, and basically at this point there is no stalling, so F1 is gone. F2 could now move to the switch allocate stage directly, because because at this point F1 is gone, and only after F1, F2 would be allocated a switch, and it is going to go, because once it's allocated a switch, it needs to traverse and go. So F2 goes to this stage, and at this point F3 comes, from the previous router. So it goes into the buffer write stage. So then what we see is that in the 7th cycle, F2 is allocated a switch port and then F2 goes away. And then goes away means it is transmitted to the next router on the way. And F3 goes to the switch allocate stage, where we see that we need to stall for one cycle. The reason being that we are not able to find a switch. So basically what happens is that this goes from here to here. So we wait for one additional cycle for the switch allocation to happen, and finally F3 gets transmitted over here in the 9th cycle. So this is somewhat of a modified diagram in the sense, as you can see, that at one point of time, right, we can have also multiple flits that are there in the same stage, which was not there earlier, even though this diagram does not show that. But you get the idea. The idea basically is that we have a strict sequentialization of flits within a packet, and furthermore the head flit needs to go through two additional stages, which are RC and VA. But the switch allocation we are trying to do for every flit separately. But this overhead, so basically the overhead is 3 cycles for body and tail flits, and it is 5 cycles for the head flit, but the head flit determines the critical path. That is why reducing these 5 cycles is important. So let us look at one of the most common optimization techniques called Lookahead routing, where essentially you compute the route for the next hop. So let us say that this is the route that a path will take, 1, 2, 3, 4, 5 nodes, 1, 2, 3, 4, 5. So what I do is that initially I see where am I supposed to go. So node 1 will tell you that I am supposed to go to node 2. So the idea here is that you maintain some of the state that node 2 would maintain, which it can periodically also transfer. At node 1, you make a decision as to what node 2 should compute, in the sense where should node 2 actually send the packet, right, which way. So node 1 is essentially computing the decision that node 2 will take, even though you may argue that this would be a bad idea because it does not have all the information that is available to node 2, like congestion information and so on. But again, they are kind of close by, and node 2 can also periodically relay information to node 1. But we will see it serves an important purpose. And similarly, when the packet comes to node 2, then node 2 knows already, kind of a priori it knows that it needs to send it to 3. So the route computation as such is now off the critical path, right, it is off the critical path. What node 2 would do is it would basically compute the decision that node 3 will take, and pretty much when the head flit comes, it will basically tell node 3 that look, it has already been pre-decided and I need to go to 4. So what you need to do is that you need to compute the decision that 4 will take, so on and so forth. And the routing decision is clearly sent along with the packet. The advantage is it moves the RC stage out of the critical path, and the disadvantage is that we are kind of dealing with reduced information, insufficient information. That is the disadvantage. So if I look at these pipeline diagrams, then the original head flit, right, the original scheme in the head flit would actually traverse these 5 stages, RC, VA, SA and ST. And the body flit would, this RC and VA would not be there for the body flit. So we will write it in the buffer, allocate a switch and traverse once the head flit is gone. In Lookahead routing, basically VA and RC can be done in parallel. RC is not in the critical path anymore. So 5 has been reduced to 4. And for the body flit, it remains more or less the same because these 2 stages will not be there. We buffer write, switch allocate and switch traversal. So we have made an important reduction from 5 to 4 over here. Now let us look at another optimization known as bypassing. So let us assume that the queues of the router are empty, which could be the case because you don't have a lot of traffic all the time. So in that case, an attempt should be made to directly traverse the switch if we have some idea the queues of a router are empty. But of course, there should be a way for detecting conflicts where then we sort of fall back, right? Resort basically in this case would be we fall back to the conventional method. So in this case, what would happen is that of course VA and RC this needs to be done, but the buffer write stage which used to be there, that is skipped. Switch allocation stage which used to be there, that also is skipped because we directly try to take one of the free input ports of the switches and directly try to traverse, and of course we have a collision detection circuit. So pretty much what we are doing is that VARC still has to be done because we are still assuming Lookahead routing, and so both these stages have to be done, and so in this case that is required. And maybe what would have been slightly more accurate is write VA over here and write RC over here to indicate that it's still not in the critical path, but you get the idea. So in this case, if the queues are empty, then our 5 has pretty much been reduced to 2. So just traversing a router for the head flit has become something which is very easy, which has pretty much been reduced from 5 cycles to 2 cycles for the head flit, which is what matters. But again, what is the likelihood of finding all the queues to be empty? Well, that needs to come out through simulation studies, which we will look at later. Another approach is speculative VC allocation, where you assume that you will find a free virtual channel, right? Whether that is the case or not, well, this is something that you are kind of speculating, guessing. But the idea is, since you are assuming that, what you do is after finding a free VC, you send this information along with the head flit. So I'll just explain in a second how this works. If of course the speculation is wrong, you always kind of fall back to the conventional method, which is your 5-stage pipeline. So the fallback option in the case of a speculation or a prediction failing, that option is always there. That is always available to you. But in this case, where there is some amount of slack, some amount of emptiness in the queues, let's say, right, some amount of slack, you would like to optimize. So what you do is you still have lookahead routing, so RC is off the critical path. Now what you do is you try to take virtual channel allocation out of the critical path. So you say that, look, let me first write it into a buffer, let me try to allocate the switch, and this will take anyway 1 cycle to find a switch. At that point of time, I do lookahead routing, which was not on the critical path anyway. I do virtual channel allocation, which was not on the, which in this case is not on the critical path. All right. Now the idea here is, if I find a virtual channel, then basically, which is free, then I stamp the head flit with whatever, stamp means I write the virtual channel that I just allocated to the head flit and I make it pass through the switch. If I don't find a virtual channel over here, then essentially I stall this process and then I go through the traditional route, which is that I wait for a virtual channel to be allocated, and once a virtual channel is allocated, right, I do switch allocation once again, and then I do switch traversal once again. So the key point is that here we are making an important guess, and the guess is that I will find a free virtual channel allocation. Hence, I am saying that, look, go ahead and allocate a switch port, and in the meanwhile, I will find a free virtual channel, which in all likelihood I will be able to find one, or let's say with high probability I will be able to find one. Once I find one, I will take that information and I will stamp the packet, and you go through. In case it doesn't go through, you fall back to what you are doing. So this, as you can see, also reduces us from 5 to 3 cycles. It is not as aggressive as bypassing, in the sense it still has the buffer write stage. It's somewhat less aggressive, but making a guess that you will find a free VC is somewhat more reasonable than assuming that the queues are empty. So this is somewhat more practical than pure bypassing. Another idea is late VC selection, where what we do is that the virtual channel allocation happens along with switch traversal, right? So we maintain a queue of free virtual channels with each outgoing link. So the moment you are, let's say, going on a certain link, you maintain a small queue of free virtual channel IDs. The moment the head fleet is traversing the switch, at the same time we kind of pick an element from the queue and assign it a VC. In the sense, the moment it kind of emerges from the other side of the switch, we write this information and send it down the link. The main problem is, what if a free VC is not available and the queue is empty? Well, if the queue is empty, we will know that earlier also, in the sense that maybe 2 cycles before that, if we see that the queues are empty for a certain outgoing link, we will not even try to allocate a switch. But of course, race conditions are possible where another another head fleet kind of takes a VC and runs away. So in case that happens, we have a small circuit to detect this, and we can always restart the conventional 5-stage process. So that fallback option is always there with us. So in case at this point we find that we are not able to allocate a VC, we just cancel the process of sending the fleet and we go through the normal conventional routine of 5 stages, right? So that option is always there. But again, this is also a neat way of removing VA from the critical path, because you are saying that, look, in all likelihood I will find a free VC, so why not I maintain a queue and then finally pluck an entry from the queue and go. Kind of in principle similar to speculative VC allocation, even though the mechanism is quite different. So we have seen this picture before also. I will not spend a lot of time, we had seen it in a previous lecture. So I will maybe quickly go through it once again. So basically we have 5 incoming links from north, south, east, west and local, assuming multiple VCs per link. This is the buffer write stage, and then of course we write it to a buffer, we compute the route. So as I said, this itself could be moved off the critical path using Lookahead techniques. Then we do VC allocation, which itself can be moved off the critical path, assuming either speculative VC allocation or late VC allocation. Finally, we allocate a switch port and we traverse the switch, and of course a large part of this also can be removed with direct traversal, right, as we have seen in the case of bypassing, that we can do these VA-RC computations and just traverse the switch. And for the rest of the packets, the flits in the packet, we can directly do switch traversal, assuming that the router is totally empty. For them, the router latency is actually 1 cycle. But again, as I said, the likelihood of this happening is, well, could be high, could be low, it's very benchmark dependent. So with this, this lecture finishes. So we'll have a last lecture where we will discuss 2 things primarily. One is that how do I co-design the cache architecture with the NOC, right, NOC and cache, and how do I measure the performance of an NOC, right, what is the standard way of measuring how good or how bad an NOC performs.